Propositional calculus is the branch of mathematical logic concerned with the study of propositions that are formed by other propositions with the use of logical connectives, and how their value depends on the truth value of their components. Logical connectives are found in natural languages. In English, for example, some examples are and, or, not, and, if. The following is an example of a very simple inference within the scope of propositional logic. Premise 1. If it's raining then it's cloudy. Premise 2. It's raining. Conclusion. It's cloudy. Both premises and the conclusion are propositions. The premises are taken for granted and then with the application of modus ponens the conclusion follows. As propositional logic is not concerned with the structure of propositions beyond the point where they can't be decomposed anymore by logical connectives, this inference can be restated replacing those atomic statements with statement letters, which are interpreted as variables representing statements. Premise 1. Premise 2. Conclusion. The same can be stated succinctly in the following way. When P is interpreted as, it's raining, and Q as, it's cloudy, the above symbolic expressions can be seen to exactly correspond with the original expression in natural language. Not only that, but they will also correspond with any other inference of this form, which will be valid on the same basis that this inference is. Propositional logic may be studied through a formal system in which formulas of a formal language may be interpreted to represent propositions. A system of inference rules and axioms allows certain formulas to be derived. These derived formulas are called theorems and may be interpreted to be true propositions. A constructed sequence of such formulas is known as a derivation or proof, and the last formula of the sequence is the theorem. The derivation may be interpreted as proof of the proposition represented by the theorem. When a formal system is used to represent formal logic, only statement letters are represented directly. The natural language propositions that arise when they're interpreted are outside the scope of the system, and the relation between the formal system and its interpretation is likewise outside the formal system itself. Usually in truth-functional propositional logic, formulas are interpreted as having either a truth value of true or a truth value of false. Truth-functional propositional logic in systems isomorphic to it are considered to be zeroth-order logic. History. Although propositional logic had been hinted by earlier philosophers, it was developed into a formal logic by Chrysippus in the 3rd century BC and expanded by the Stoics. The logic was focused on propositions. This advancement was different from the traditional syllogistic logic, which was focused on terms. However, later in antiquity, the propositional logic developed by the Stoics was no longer understood. Consequently, the system was essentially reinvented by Peter Abelard in the 12th century. Propositional logic was eventually refined using symbolic logic. The 17th, 18th century mathematician Gottfried Leibniz has been credited with being the founder of symbolic logic for his work with the calculus ratiocinator. Although his work was the first of its kind, it was unknown to the larger logical community. Consequently, many of the advances achieved by Leibniz were re-achieved by logicians like George Boole and Augustus de Morgan, completely independent of Leibniz. Just as propositional logic can be considered an advancement from the earlier syllogistic logic, Gottlob Frege's predicate logic was an advancement from the earlier propositional logic. One author describes predicate logic as combining the distinctive features of syllogistic logic and propositional logic. Consequently, predicate logic ushered in a new era in logic's history. However, advances in propositional logic were still made after Frege, including natural deduction, truth trees and truth tables. Natural deduction was invented by Gerhard Ganson and Jan Łukasiewicz. Truth trees were invented by Evert Willem Beth. The invention of truth tables, however, is of controversial attribution. Within works by Frege and Bertrand Russell, one finds ideas influential in bringing about the notion of truth tables. The actual tabular structure itself is generally credited to either Ludwig Wittgenstein or Emil Post. Others credited with the tabular structure include Lukasiewicz, Schroeder, Alfred North Whitehead, William Stanley Jevons, John Venn, and Clarence Irving Louis. Ultimately, some have concluded, like John Shosky, that it is far from clear that any one person should be given the title of inventor of truth tables terminology. In general terms, a calculus is a formal system that consists of a set of syntactic expressions, a distinguished subset of these expressions, plus a set of formal rules that define a specific binary relation, intended to be interpreted to be logical equivalents, on the space of expressions. When the formal system is intended to be a logical system, the expressions are meant to be interpreted to be statements, and the rules, known to be inference rules, are typically intended to be truth-preserving. In this setting, the rules can then be used to derive formulas representing true statements from given formulas representing true statements. The set of axioms may be empty, a non-empty finite set, a countably infinite set, or be given by axiom schemata. A formal grammar recursively defines the expressions and well-formed formulas of the language. In addition, a semantics may be given which defines truth and valuations. The language of a propositional calculus consists of a set of primitive symbols, variously referred to be atomic formulas, placeholders, proposition letters, or variables, and a set of operator symbols, variously interpreted to be logical operators or logical connectives. A well-formed formula is any atomic formula, or any formula that can be built up from atomic formulas by means of operator symbols according to the rules of the grammar. Mathematicians sometimes distinguish between propositional constants, propositional variables, and schemata. Propositional constants represent some particular proposition, while propositional variables range over the set of all atomic propositions. Schemata, however, range over all propositions. It is common to represent propositional constants by B and C, propositional variables by P, Q, and R, and schematic letters are often Greek letters, most often phi, psi, and chi. Basic concepts. The following outlines a standard propositional calculus. Many different formulations exist which are all more or less equivalent but differ in the details of their language, that is, the particular collection of primitive symbols and operator symbols, the set of axioms, or distinguished formulas, and the set of inference rules. Any given proposition may be represented with a letter called a propositional constant, analogous to representing a number by a letter in mathematics. For instance, r equals 5. All propositions require exactly one of two truth values, true or false. For example, let P be the proposition that it is raining outside. This will be true if it is raining outside and false otherwise. We then define truth functional operators, beginning with negation. P represents the negation of P, which can be thought of as the denial of P. In the example above, P expresses that it is not raining outside, or by a more standard reading, it is not the case that it is raining outside. When P is true, P is false, and when P is false, P is true. P always has the same truth value as P. Conjunction is a truth functional connective which forms a proposition out of two simpler propositions, for example, P and Q. The conjunction of P and Q is written PQ, and expresses that each are true. We read PQ for P and Q. For any two propositions, there are four possible assignments of truth values. P is true and Q is true, P is true and Q is false, P is false and Q is true, P is false and Q is false. The conjunction of P and Q is true in case 1 and is false otherwise, where P is the proposition that it is raining outside and Q is the proposition that a cold front is over Kansas. PQ is true when it is raining outside and there is a cold front over Kansas. If it is not raining outside, then PQ is false, and if there is no cold front over Kansas, then PQ is false. Disjunction resembles conjunction in that it forms a proposition out of two simpler propositions. We write it PQ, and it is read P or Q. It expresses that either P or Q is true. Thus, in the cases listed above, the disjunction of P and Q is true in all cases except 4. Using the example above, the disjunction expresses that it is either raining outside or there is a cold front over Kansas. An example of the exclusive or is, you may have a bagel or a pastry, but not both. Often in natural language, given the appropriate context, the addendum, but not both, is omitted but implied. In mathematics, however, or is always inclusive or, if exclusive or is meant, it will be specified, possibly by XOR. Material conditional also joins two simpler propositions, and we write PQ, which is read, if P, then Q. The proposition to the left of the arrow is called the antecedent and the proposition to the right is called the consequent. It expresses that Q is true whenever P is true. Thus, it is true in every case above except case 2, because this is the only case when P is true but Q is not. Using the example, if P then Q expresses that if it is raining outside then there is a cold front over Kansas. The material conditional is often confused with physical causation. The material conditional, however, only relates to propositions by their truth values, which is not the relation of cause and effect. It is contentious in the literature whether the material implication represents logical causation. Biconditional joins two simpler propositions, and we write PQ, which is read P if and only if Q. It expresses that P and Q have the same truth value, thus P if and only if Q is true in cases 1 and 4, and false otherwise. It is extremely helpful to look at the truth tables for these different operators, as well as the method of analytic tableaus. Closure under operations. Propositional logic is closed under truth functional connectives. That is to say, for any proposition phi is also a proposition. Likewise, for any propositions phi and psi is a proposition, and similarly for disjunction, conditional, and biconditional. This implies that, for instance, phi is a proposition, and so it can be conjoined with another proposition. In order to represent this, we need to use parentheses to indicate which proposition is conjoined with which. For instance, PQR is not a well-formed formula, because we do not know if we are conjoining PQ with R or if we are conjoining P with QR. Thus we must write either R to represent the former, or P to represent the latter. By evaluating the truth conditions, we see that both expressions have the same truth conditions. This means that conjunction is associative. However, one should not assume that parentheses never serve a purpose. For instance, the sentence P does not have the same truth conditions of R, so they are different sentences distinguished only by the parentheses. One can verify this by the truth table method referenced above. Note: for any arbitrary number of propositional constants, we can form a finite number of cases which list their possible truth values. A simple way to generate this is by truth tables, in which one writes P, Q, Z, for any list of k propositional constants, that is to say, any list of propositional constants with k entries. Below this list, one writes 2k rows, and below P1 fills in the first half of the rows with true and the second half with false. Below Q1 fills in 1/4 of the rows with T, then 1/4 with F, then 1/4 with T and the last quarter with F. The next column alternates between true and false for each 1/8 of the rows, then 1/16ths, and so on, until the last propositional constant varies between T and F for each row. This will give a complete listing of cases or truth value assignments possible for those propositional constants. Argument. The propositional calculus then defines an argument to be a set of propositions. A valid argument is a set of propositions, the last of which follows from, or is implied by, the rest. All other arguments are invalid. The simplest valid argument is modus ponens, one instance of which is the following set of propositions. This is a set of 3 propositions, each line is a proposition, and the last follows from the rest. The first 2 lines are called premises, and the last line the conclusion. We say that any proposition C follows from any set of propositions, if C must be true whenever every member of the set is true. In the argument above, for any P and Q, whenever P, Q and P are true, necessarily Q is true. Notice that, when P is true, we cannot consider cases 3 and 4. When PQ is true, we cannot consider case 2. This leaves only case 1, in which Q is also true. Thus Q is implied by the premises. This generalizes schematically. Thus, where phi and psi may be any propositions at all, other argument forms are convenient, but not necessary. Given a complete set of axioms, modus ponens is sufficient to prove all other argument forms in propositional logic. Thus they may be considered to be a derivative. Note, this is not true of the extension of propositional logic to other logics like first-order logic. First-order logic requires at least one additional rule of inference in order to obtain completeness. The significance of argument in formal logic is that one may obtain new truths from established truths. In the first example above, given the 2 premises, the truth of Q is not yet known or stated. After the argument is made, Q is deduced. In this way, we define a deduction system to be a set of all propositions that may be deduced from another set of propositions. For instance, given the set of propositions, we can define a deduction system, gamma, which is the set of all propositions which follow from A. Reiteration is always assumed, so, also, from the first element of A, last element, as well as modus ponens, R is a consequence, and so, because we have not included sufficiently complete axioms, though, nothing else may be deduced. Thus, even though most deduction systems studied in propositional logic are able to deduce this, one is too weak to prove such a proposition. Generic description of a propositional calculus. A propositional calculus is a formal system, where the alpha set is a finite set of elements called proposition symbols or propositional variables. Syntactically speaking, these are the most basic elements of a formal language, otherwise referred to as atomic formulas or terminal elements. In the examples to follow, the elements are typically the letters P, Q, R, and so on. The omega set omega is a finite set of elements called operator symbols or logical connectives. The set omega is partitioned into disjoint subsets as follows. In this partition, is the set of operator symbols of arity J. In the more familiar propositional calculi, omega is typically partitioned as follows. A frequently adopted convention treats the constant logical values as operators of arity 0. Thus, some writers use the tilde, or n, instead of, and some use the ampersand, the prefixed k, or instead of. Notation varies even more for the set of logical values, with symbols like false, true, f, t, or all being seen in various contexts instead of 0, 1. The zeta set is a finite set of transformation rules that are called inference rules when they acquire logical applications. The iota set is a finite set of initial points that are called axioms when they receive logical interpretations. The language of, also known as its set of formulas, well-formed formulas, is inductively defined by the following rules. Base. Any element of the alpha set is a formula of, if a formula is in, then is a formula. Closed. Nothing else is a formula of. Repeated applications of these rules permits the construction of complex formulas. For example, by rule 1, P is a formula. By rule 2, is a formula. By rule 1, Q is a formula. By rule 2, is a formula. Example 1. Simple axiom system. Let, where, are defined as follows. The alpha set is a finite set of symbols that is large enough to supply the needs of a given discussion, for example, of the 3 connectives for conjunction, disjunction, and implication. One can be taken as primitive and the other two can be defined in terms of it and negation. Indeed, all of the logical connectives can be defined in terms of a sole sufficient operator. The biconditional can of course be defined in terms of conjunction and implication, with defined as adopting negation and implication as the two primitive operations of a propositional calculus is tantamount to having the omega set partition as follows. An axiom system discovered by Jan Łukasiewicz formulates a propositional calculus in this language as follows. The axioms are all substitution instances if the rule of inference is modus ponens, then is defined as, and is defined as. This system is used in MetaMath Set.mm formal proof database.